Our next speaker is from the University of Notre Dame. Doug's going to speak to us again on the subject of greater workflows or workflows more largely considered.
Maybe not. One moment, please. All right. So thank you for the introduction. My name is Douglas Thain from the University of Minnesota. And actually, I always appreciate coming to this because I get all sorts of new ideas and also great relief that in climate science, people ask you questions like, what's going to happen in the next 1,000 years? Because at the moment in computing, I don't know what's going to happen in the next 6 months. So, but I'm going to talk a little bit about task graphs. Oh yes, the other thing. There are two important problems in computing. Naming, caching, and off by one errors. And both of those occur when I get confused with Greg. So I've had several conversations today where somebody came up to me and said, Greg, remember that feature I asked you for? And I just said, yeah, I'll get right on it. All right, so today I want to talk about wrangling massive task graphs with VineReduce. And there's a couple words to define there. I won't bore you with the outline. Okay, so I direct a group called the Cooperative Computing Lab at the University of Minnesota. I'm a computer scientist, but I hope you won't hold it against me. And we do very applied research. So we operate computer systems. We have a pretty good sized Condor pool, which is slurping all the cycles out of our HPC system. We assist people in a wide variety of fields in designing and running workflows. We do computer science research, and we also publish software. And you probably heard me talk about a couple of these different pieces of software over the years. And they're all live and kicking. TaskVine is the focus of most of our effort at the moment. You've heard a lot about workflows. I won't belabor the point, but I want to point out exactly what we're talking about with workflows and then make a distinction with something else. All right, so I think the most common way of viewing a workflow is to say, we have a user, the user knows they have a bunch of stuff to do, and they will sit down and write out a DAG or a script that generates a DAG or something like that, where each node in that graph represents a job for Condor to do. So in that graph up there, we have circles that are tasks to run. We have squares that are files. The user puts them together. They have some idea of the shape of that. They give it to a workflow management system like Pegasus or Dagman or Makeflow or Nextflow. And that workflow management system now evaluates the DAG and passes stuff to HT Condor to do. And under that assumption, those nodes in that graph are usually fairly big things, right? So you don't submit subsequent jobs and expect the batch system to sort it out particularly efficiently. And so usually we think of those things as running from minutes to hours. And if we're going to pass files around, we're talking about megabytes to gigabytes. All right. Now, there are all sorts of variations on this workflow term. I want to introduce something that's a variation. So I want to talk about task graphs. And we see task graphs crop up in high-throughput computing, but also in high-performance computing, also in multi-threaded programs, also in GPUs. And the things I want to talk about today look like this. The end user writes a program in a functional programming language, or a data flow programming language. And that's the thing they write. And that program then is evaluated to generate a graph internally that the user doesn't see. And they kind of know it's there, but they don't really know the shape. They don't know exactly all the pieces and how they fit together. And each node in this program is not a big fat batch job, but it is a function call. A function call, and so the data items that are going back and forth are items in memory in a programming language, and that function takes in some arguments, it computes, it produces some results, and it passes along to another function until you get the output. And that kind of smells like workflows, right? There's a lot there that rhymes about workflows, but the jobs are generally smaller, faster. They have some complicated software dependencies. And often those data items are small, although sometimes you get to the end and they can be very large when you accumulate lots of things. All right, so because these things are relatively small, we usually have some overlay system on top of that. So we have a manager that dispatches these tasks to workers, because a lot of things need to be retained in memory. And then we provision those workers using a resource manager. All right, and so the tools I'm going to talk about today that fit this pattern.
So before you go, is that the graph or is that the DAG? With that
DAG is a description of a data structure, right?
no, a DAG is an hierarchically graph. So when you're saying graph, is it an arbitrary graph with loops and everything in it?
It's a DAG.
It's a DAG. It's not
DAG.
a graph.
Yeah. Now, it might be a
Because-
dynamically generated DAG.
Yeah. Everything is dynamic. I mean, what you described earlier is not the truth, because in quite a number of cases, the user talks to a script that creates the DAG. But that's a different discussion. Yeah.
Look, I didn't say that this is A and this is B and they're completely different. I said it's a variation. There's a quality
I'm
difference.
just checking here, because if it's not a DAG, then any compiler will qualify to what you said, because every step in assembly language that I don't know if you ever there is taken two inputs and add them and create an output. So every program I can create it as blue as green.
I think
so where should I stop?
I think there's a lot that rhymes. I think there's a lot that rhymes with compilers, right? And a lot of the same optimizations apply because you can.
So why do you call it why do we need workflows and data flows and all the kind of thing? It's a programming language. It is A equal B plus C divided by Q and blah, blah, blah.
Fair enough, it is a programming language, but like workflows, it's restricted in ways that are not usually common in general purpose programming.
So I cannot run Lisp here.
So you went out?
No Lisp.
No Lisp?
No, as a programming language doesn't fit here. Not fine.
Let's come back to that at the end. All right. So, quick review of data flow programming, right? So the way the user thinks about this sort of stuff is they're going to write a bunch of transformations on data, maybe with higher order operators, in which they are going to spec out the computation to be done before they execute it, right? So you declare a data set that's an input. Maybe you call some split operation to divide it into pieces. And then, hey, let's apply a function to map and then reduce to get some result here called B. Now, I want to emphasize at this point in the program, as the program's executing, nothing is really run yet. The program that you're writing generates the DAG. It hasn't actually done any of this computation anywhere on the cluster yet. And you can keep adding to this. So we can make arbitrary constructions. And then it isn't until you get to the very end that you say, hey, give me the final result, print D, that we go back and say, okay, now I've got a graph. Let me go execute it, right? So our colleagues in physics are very excited about this. I have $5 in my pocket to pay the penalty of showing a particle detector if necessary. But we've been working with folks in CMS and we're getting organized with Atlas as well to work on some data analysis applications. And what our friends in physics have come to is that, you know, your typical grad student is long past the point of wanting to write C++ that talks to root. Those days are gone. They are quite sensibly writing programs in Python that are using the scientific Python ecosystem. They write codes that look like this. That on the left there is the complete top-level program for a toy analysis that our colleagues give to the graduate students and say, start here as your analysis code. And if you squint, you can see some of the elements that I was talking about before. So up at the top there, it says dataset, get dataset. It's going to go out and fetch data from a root file. It's going to transform it into data structures that are more natural fit for the scientific Python ecosystem. And then we're going to construct a histogram, give it some operations, give it some arguments about how we want it to look at the end. And then we're going to fill it in with the events from the data source. And at the end, we say, go compute it. And internally, we get a graph that looks something like that. But the user never sees that. Well, unless I ask really hard, and they never ask because they don't want to see it, because it ends up producing graphs that take about an hour just for GraphViz to process and produce a result. By the way, I can't give a talk without a dot graph. I just love dot. I don't know if anybody feels that way. Now, Dask is awesome. Sorry, I gave away the punchline here. Dask is awesome for local computation. And it's awesome for local computation because it's using the scientific Python ecosystem. We can do our own matrix multiplies and all our vector operations, and it takes advantage of all the smart things you can do with local CPUs in terms of vectorization. It takes advantage of multiple threads. If it's using NumPy, then it goes on the GPU. And if you're running something that fits locally, bam, 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 it computes it. It's awesome. Now, Dask does have a distributed option, but if you've ever used it, it's not great. I'm sorry, is there a Dask person here? Good, right. If you've ever used it, it's not great. Because it wasn't really designed for high throughput computing. It doesn't deal well with failures. It doesn't deal well with different granularities. It doesn't deal well with heterogeneity. And so once you get above a certain size, it just doesn't work. And so if you take this, even this toy application and try to run it on 10 nodes in the cluster, it gets stuck, it doesn't finish. And in fairness, I think that's because really the attention of the developers has been on the local experience. But our friends really like this mode of computation, and we want to give them a way to do it. So we'll bring in TaskVine, which is our workflow execution system. And TaskVine handles data-intensive, high-throughput, large-scale task graphs like this. It has some neat features. So you can have a bunch of heterogeneous workers that it will slice and dice and pack in tasks, whether they're big or small, to use the appropriate resources. Often you don't know the appropriate resources. So if you just say, here's a task, figure it out for me, it will take a bunch of related tasks and determine, you're supposed to be using a GPU and this thing needs 2 cores and 4 gigabytes of memory, and right-size them for you. You can intermix Unix executables and functions as a service computing. It handles data management and replication, failures, and all that sort of stuff. And it works really well with HT Condor. So it's very easy to deploy TaskVine on top of a cluster. And you get something like this. So we have the end user on the left is going to write their program in just the normal Dask way. They press compute, it generates a graph, and we pass that graph off to TaskVine. And TaskVine starts doling out the pieces to each of the workers and handling the data transfer and pulling stuff from remote services. And because these resources are opportunistic, it doesn't get too upset if workers come and go. And we can run some very large scale applications this way. I think I'll skip very briefly. This is how TaskVine intermixes conventional executables with installed functions and invoking them. But I think I'll move past that. All right, so our friends have this data analysis application called DV5. And once we got all this set up and hooked together, we get this beautiful characteristic curve of tasks running. And so we have the graduate students regularly running on 6,000 cores, 2/3 of an hour. Over there is the histograms that they get back of momentums and jet B tags. And I'm not a physicist, so I don't really know what that means, but they tell me it's good. So we're done, right? No, we're not done. One of the hazards of supervising graduate students is they often don't tell you all the things because they haven't yet internalized the things that are important. So we have this application, it runs in about an hour. And I said, that's really awesome. Can you run it for me again and bring me the results in about an hour? It was going to tweak something and produce another graph. And the student sort of scratched his head and said, well, I can bring it for you tomorrow. Why tomorrow? Are you going out? Are you on vacation? Or what's that? Well, when I run the application, it sits there for about 6 hours, and then it does that. You think you solved the right problem. All right, so what? Why is this the first time you're telling me this? And it's not just this particular application. So we have a colleague at the University of Florida who wants to run a gigantic application here called Cortado. Again, we couldn't plot the whole thing, but this is 1/400th of the graph. And she wants to process 12 billion events over 14 terabytes, and pressed go, and it sits there for 20 hours generating the graph before any computation happens. So I'm kind of embarrassed by this. Well, so what's going on? We got to go back to the top. We got to go up to Dask. So what's happening as you're programming this thing, right? So you're writing these functions that add to the graph incrementally and as they go. And every time you add something to the graph, well, you have to update the dependencies and the nodes and the arcs, and you have to check the types on this and the types on that, and you have to do a malloc and all this sort of stuff. And so if you have just a handful of nodes, the construction's pretty quick, but it goes up with this huge linear factor as you increase the number of things that you are processing. So it's sort of ridiculous that creating the graph starts to rival the execution time. Now you might say, Doug, come on. It's a couple 100,000 things. How long does it take to add them to the graph? Well, it's not just 180,000 mallocs. It's 180,000 log events. And it's 180,000 stats of files. And it's 180,000 everything, right? So Marone, I know you're going to jump up and say, today I can Condor submit 180,000 things, but it's all the stuff that goes with that blows up the cost. All right, so we played some games and we tried to optimize a few things, and we got that orange line there, which is a little better. And so, yeah, okay, maybe we can optimize things a little bit, but we really don't want 180,000 of all the things. Now, I should give credit here to a member of my team, Ben Tovar, who plotted the entire dot graph and went away for an hour and meditated on the mess of stuff on the screen. He says, you know, I don't think that this is an arbitrarily structured DAG. I think there's a hierarchy here, and I think that we can take advantage of it. And he went away and he sketched a picture like this. He said, what we have here is a MapReduce. Who knows about MapReduce? Bunch of people. Okay, so you know what MapReduce is great, right? Nice, handy abstraction for doing things. It's a MapReduce at the top level because we're processing each of these data sets and then reducing something as a result. And each node in that MapReduce is a MapReduce. And then each node in that inner MapReduce is a 1,000-node task graph. Okay, so we're getting some here. We're making some progress. There is a hierarchy. And maybe if we design a system that respects the hierarchy of the thing that we're trying to process, we can do a better job so we don't have to do 180,000 of all the things up front. So he said, okay, in a MapReduce style, let me get the things that you need to do to specify your physics application. And we took a little inspiration here from the coffee framework that does something similar, but we added a few new pieces here. And so the idea is the user is going to specify a pre-processing and a post-processing, a processor and a reducer, put them all together and say, VineReduce me some data. Now the interesting thing here is we're still going to use Dask. We're still going to use Dask in the processor part, on the part that goes on the local node, because Dask is awesome there, and we want to exploit that capability. So we're going to give all the pieces to VineReduce, and VineReduce is going to materialize them as needed. Actually, that's a real application there, most of it anyway. So, you know, just sort of standard Python data structures sort of stuff. All right, so let me explain architecturally what's going on here. In the traditional way of thinking, we would say, all right, we're gonna make a DAG. We're gonna make the whole DAG. And now our DAG scheduler here is gonna take one piece at a time and send it out to be scheduled. And that works. It works for a lot of things, but then you get 180,000 of all the things. Not to mention the graph construction time.
But
the other thing that happens,
truth in advertisement, DAGs were always recursive. So what you're describing here is misinformation. You can start by saying a DAG is two nodes, where each node is a DAG, where each node in the DAG is a DAG.
Okay,
okay, and you don't schedule the whole DAG when you start it, and you can actually modify the sub-DAGs as the DAG is going. So please, truth in advertisement, Doug.
We'll get there. So
we are there already.
So what ends up happening is you get individual nodes scheduled to your workers. And also, this isn't the best way of using your multi-core workers either, right? Because you have this problem of dispatching each individual one core thing, there are better ways to do it. So what we end up with here is a dynamic hierarchy. You don't expand the whole thing at once. The analogy I like to make is you have a big block of cheese representing your data. Greg doesn't like this analogy. You have a big block of, I'm in Wisconsin. You have a big block of cheese representing your whole data, and you slice off enough of the cheese as you think you can materialize at once.
We love cheese curds.
See, now we're on the right track. All right, so up at the top, we have all the data sets that you want to process. We don't materialize all of them at once. Some of them are pending, some of them are done, some in the middle are processing. For each data set that's running, now we're going to take that and divide it up into the files. Some of them are pending, some of them are processing, some of them are done. We only materialize as many as we can actually handle. For those that we're actually going to run, for those that are actually ready to run, we materialize tasks, and those tasks consist of task graphs, and then we take those task graphs and we run them on the worker, and we run them as big fat tasks that consume a large number of cores, and then we parallelize inside of them and get all the task goodness. All right, so a couple benefits here. So one is your setup time basically disappears, right? Because you're not materializing all the things. You never get 180,000 things at the top level, right? You only get your pieces of the hierarchy. The user still gets some reasonable progress bar about what's being accomplished. And it's also because we're sending the DAS programs out to the nodes, even if there was some remaining inefficiency, that gets distributed. And the other thing is you end up using your resources more effectively. So on the left side here, we have the old system. Blue means a task is actually processing effectively. Orange means we're waiting for something. So on the left here was the old way of dispatching individual one-core tasks. Here's the new way of dispatching those big fat DAS tasks. This was a smaller run that only took 7 minutes. All right, so we go back to our colleagues here. Instead of sitting around for 20 hours waiting to generate, she's still writing the same DAS code. She's still writing the same underlying code. We provide a little organization framework to it, and now we can chew through this thing in 5 hours, right? So the computation time is about a quarter of what the setup time was before. All right. Now, some ruminations, coming back to the hierarchy. And I think Frank brought this up earlier. There is a hierarchy to the hardware. There's a hierarchy to the hardware, right? You've got cores in a chip, you've got chips on a node, you've got GPUs, you've got nodes, you've got racks, the ideal case is when the hierarchy of the software is matched to that of the hardware, but that's often only the case if somebody wrote the application with that hardware in mind, building it up just so. Sometimes the application comes as given and we have to figure out what that hierarchy is at runtime in order to decompose it appropriately. VineReduce is a static framework. We said, this is the structure, plug in your things. And you know what? That's the conservative thing to do to make one particular use case run well. I would like to get to a place where you can say, we have this gigantic DAG to be run. Can I carve off 100 of those things, make that a dynamically chosen sub-DAG, and throw that over the wall for execution? There's all sorts of programming language theory that I think we would be well to learn from in the workflows world. So a lot of things I've been talking about here relate to lazy versus eager evaluation. They relate to higher order functions and how we go about evaluating them. There was some other thing I was going to mention. We need to go back to talk to Tom Reps in 704 and bring him in here and say, what can we learn? And it's different because the costs are different in distributed computing. But I think there's some good old time stuff from Lisp and friends that we should be using here. Finally, something I'm worried about here is the increasing distance between the user and the resource consumption. So our colleagues in physics are already in the mode of saying, look, I'm going to write a prompt for my application. Write for me a Dask application that takes this 10 terabytes of data and finds the electron-electron collisions and throws out the ones that are green. I'm not a physicist. And then it writes some Dask code. And so the LLM generates a functional program, and the functional program generates a Dask, and the Dask runs, and the DAG runs a task, and the task run on the workers. And then when everything catches fire, how do we impute our problems from the bottom to the top? I don't have an answer for that. I think the LLM folks say we're going to have a lot of logs and we're going to parse them all, to which I say, good luck. Yeah, so I think that brings me to the end. if you're interested in TaskVine, I'd be happy to talk to you more about it. We're always looking for new collaborators and applications. Well, last release was last week. You can check it out online. You can Conda install it. I want to thank all my students and NSF for funding this work, and I'll be happy to take questions from anybody else.
Mine were not questions, but
So first of all, I'm going to abuse my moderator privilege and say, I think your cheese metaphor has holes in it. And on a serious note, in the functional programming world, we have all kinds of operators.
Yeah.
We have not just map and reduce, but accumulate and scan and inner product and outer product and all these things. Going back to the 2010s, with MapReduce, we've only seen lots of use of two functions, map and reduce. Do you think these other functions are useful? Or do you think that the nature of the job or task or the chunky nature, the high latency means that those operators are not useful?
Well, okay, so I think that there is actually a very subtle and beautiful reason why MapReduce is very effective. And it's not just about the structure, it's about the resource and performance assumptions of the program, right? MapReduce is glorious. Maybe I'm overselling it here. MapReduce is pretty good because you expect that all the maps are likely to be the same, right? You expect that they're all going to run the same code. You expect that they're all going to have approximately the same resource consumption. And so once you've run one, you know what to do with the rest of them. And furthermore, you know that the reduce is going to stink. And so you'd better schedule that to the biggest, fattest thing you have, and you know it's going to be last. So you better over allocate and ensure its success. And so I think that MapReduce is a success because it speaks to partitioning your workload very clearly, and it sort of forms a contract between the user and the system. Now, I think that we could write programs that consist of ASTs of all these generators, such that you get to one of these generators and then you evaluate it dynamically and keep track of your state as you go. The hazard, I think, is that if you make a big nested thing, now it's not so clear how to partition your resources in your effort across those things, right? Because the map at the top level is not the same as the map at the bottom level. So I don't have answers to all those things, but that's sort of where I think we're going and what the hazards are.
Thank you. I think we have questions from the floor. Yeah, Brian, you want to start?
So, if the whole thing comes crashing down on you, is there any point in the graph where you checkpoint and can recover? Or is the idea that this is all transient and you start from the beginning, or where's recoverability or where?
Yeah, there's a couple. Greg, would you just flip back to some slide that has a graph on it? Let's go back to, keep going. Keep going, keep going. Yeah, so no, board.
I think that's a tag.
That's the one. Yeah, so there's checkpointing at a couple levels. At the upper levels, it looks like more conventional checkpointing because you have kind of natural stopping points. You can say, how far did I get and what are my results? So there's checkpointing happening on there. It's adaptive because there's a reasonable cost to it. And so we sort of adjust the checkpointing interval as we go. When we get into the graphs down at the bottom, these are sort of interesting because they can have intermediates that remain out on the cluster. And so one of the hazards is that if you leave intermediates cached, the intermediates can get lost before you go back, before you are able to consume them. In that case, we detect their loss and then we issue compensating tasks. And that works great until your rate of loss exceeds your ability to complete the compensating tasks, in which you end up with an explosion of compensating tasks. And honestly, we haven't quite found the right hysteresis for that yet. So that's a challenge remaining. Did I answer your question?
I think there's a question from Colin.
Yeah, the story about the huge setup times for the DAG rings incredibly true in the Ruben world, and we'll tell you stories about that offline. But
love to.
Getting at the structure, the hierarchical structure that you're you're exploiting. Like you said, okay, the outside is MapReduce and the inside is this inner messy thing. But like, to what extent does MapReduce, is that like required for, like, to what extent is that actually depending on MapReduce being the outer part and the messy thing being something inside? Like, do we need MapReduce to be able to take advantage of this type of hierarchical structure, or like do we just need some way to like identify like the outer edges of this inner messy thing without having to evaluate the whole inner messy thing? Like,
Yeah.
I'm trying to figure out what's the key thing we need here.
Yeah, so it's also a question of usability, you know, and I think the analogy that I would make is go back to your basic compiler. What's the better way to parallelize a loop? Is it for the user to say, here's a loop, do whatever you want, and the compiler kind of has to work backwards and say, well, can I run these concurrently? Are there any dependencies? Or is it better for the user to say, here's a parallel for, now go parallelize it, right? So is it the user expressing that it is a MapReduce, or is it the machine inferring that's a MapReduce? Now, 20 years ago, I would have told you expressing is absolutely the right thing to do, because inference is complex and slow and hard. But you know, today we have compilers that are pretty darn awesome at finding and parallelizing loops and all sorts of things. And so maybe inferring isn't as crazy as I thought it would be 20 years ago. I wanted to clarify, I'm sorry, I did this in the wrong order. I wanted to clarify one thing. When I talk about MapReduce, I'm talking about the general concept of MapReduce. I'm not talking about a specific implementation.
Yeah.
If somebody asked, could you just stuff this into Hadoop and would it work? The answer would be no, because either Hadoop is going to be MapReducing the thing at the top and creating a mess on each node,
Right.
or it's going to be holding it all back, and that's it, yeah. So you can't just stick it in Hadoop.
So just one comment based on experience with MapReduce.
Yeah.
You know the size of the input.
Yep.
You know the size of the end of the reduce.
Yep.
You have no idea what is the size of the map.
Amen.
And when we tried in the heydays where everyone was map reducing everything,
Yeah.
you are running it in a multi-user setting, you deadlock.
Yeah.
Because you don't finish the mappers, you cannot start the reducer. So in all these discussions, I'm just making a comment, I'm not asking a question.
Well, I'll give you an answer.
Is the resource consumption of all these different elements is non-trivial, and when rather all you are doing is a demo to your advisor, then the world looks very different than what it happens in reality. So before we all get into back into MapReduce.
Okay, I understand. MapReduce is a useful thing. It is not the only thing. Now, this is where I think we have a handle on things. In these sort of workflows, we rely on the user not to tell us the resources, but rather to say, these things are of a kind, that these things are similar. And so, if we can get a few of them done, then we can characterize their behavior. And if they are indeed similar, then we have a hope of resource management in the middle. Is it a guarantee? No, there are no guarantees. But it gets us in the right direction.
The question is going back to the previous, is the likelihood of a researcher that tells you that everything is similar an event that happens once in 1,000 years? Because what we see is that a lot of these things are data dependent and they are not similar, and then you have outliers and life is getting interesting.
Agreed.
Okay, let's give Doug a round of applause.